Okay, so just when you thought we were done with equilibrium constants, you were wrong. We have one more. This one is called the solubility product constant. So if you remember back in, I want to say November, we're talking about solubility rules and how certain things form solids and certain things don't. They dissolve in water really well. Well, technically, every solid dissolves in water a little bit, some more than others, and that's where this comes in. The solubility product constant tells you how much solid will dissolve, which is actually kind of important if you think about it. I mean, you know, coral reefs are made out of calcium carbonate. It's pretty insoluble, but some of it does dissolve, and there are certain things that can shift that equilibrium, that dissolving equilibrium one way or the other. Well, then, you know, the coral reefs are gone. If they all dissolve, they're going to be gone. So it's kind of an important concept. So the way they do KSP is, generally speaking, they talk about how much solute, how much of the solid per volume of the solution will dissolve. So we're going to stick with moles per liter on these guys. And the KSP, the solubility product, is an equilibrium constant that describes how soluble it is. So things like NaCl. It's like an enormous number. NaCl dissolves really well in water. But like I said, things like calcium carbonate don't do so much, but they do a little bit. Every solid dissolves a little bit in water. And solubility is a description of how much of it will dissolve, and that is created or calculated from the KSP. So the concept behind it is it describes the solubility of a salt at a particular temperature, and it depends on how the solid dissociates. And we're talking about ionic solids here, things that have positive and negative charges. So we're going to kind of refer back a little bit to some old stuff from Chapter 7, dealing with double replacement reactions, ions, charges, things of that nature. And it works like any other KEQ that you guys have seen. Products raised to their coefficient divided by reactants raised to their coefficient. But in these problems, in KSP, the reactants are all solids, which means they aren't included. Okay? So first of all, we're going to write the balanced chemical equation in the KSP to describe the dissolving of the following salts. So all you do is you write AgCl, and I usually write an S just to remind me that it's a solid. Break it apart into the ions of which it is made. That means silver with a positive charge and chloride with a positive charge. And I write AQs because we're talking about dissolving. The KSP is done just like before. Ag raised to its coefficient, which is 1, multiplied times Cl raised to its coefficient, which is 1, divided by the reactants, except my reactant is always going to be a solid. Always for a KSP. So that's my expression right there. BaSO4 is going to break apart into the ions of which it is made. So barium. And then SO4 is called sulfate. It's on the back of your periodic table. Those are both aqueous. So the KSP expression is Ba2 plus times, SO4, 2 minus, both of them raised to their coefficients, which are both 1. And again, solid, not included. PbCl2 breaks apart into Pb2 plus and 2 chlorides, okay, both of which are aqueous. Kind of implied when it has a charge on it that it's aqueous, but I'm just going to write it in there. The KSP expression is Pb2 plus raised to its power, which is 1, times chloride, which raised to its power, which is 2. You have to remember that. Okay, it's been a while since we've done those kind of problems, but don't forget, when you set up an equilibrium constant, you always include the coefficients as a power. So now, when it comes to solving these solubility equilibria problems, you're always going to write that reaction. That means break them apart into the ions. I don't care if you write AQ or not, but if you put the charges, I think your life will be a little easier. You want to set up the KSP expression, which we just did on the previous slide. And then you're going to set up an ice table. So you thought they were done. You were wrong. Ice tables are not done. You're going to set up an ice table. You're going to put an X under the reactant, which will always be a solid. So you're not going to worry about it. We're not going to do anything with it. And you're going to solve for, if they give you the KSP, they're going to ask you to solve for the solubility. And that'll be in molarities. Or they'll give you the molarity, and they'll ask you to calculate the KSP. But it's done just like any other ice table. So AgI has that KSP, calculate the solubility. So start with the reaction, AgI, and again, I put a little solid there just to remind me. Ag plus and I minus. You don't have to write the AQ part. I'm going to set up our ice table. Big X underneath that solid because it's not important. This starts out at 0. This starts at 0. They're both going to gain. And then you have to look at the coefficients to figure out how much they are going to gain. Well, we don't know, but we're going to call it X. And since it has a coefficient of 1, it's 1X and 1X. So at equilibrium, I got X and X. My KSP expression is Ag plus times I minus. I get 1.5 e to the negative 16 equals X times X, or X squared. So I'm going to take the square root of both sides. So that's the button. If you have a graphing calculator, it's written right above the X squared button. And you get 1.22 e to the negative 8 molarity. And that is the solubility. When you solve for X, that is the solubility. You can go ahead and put it in here if you want. It might ask you, what are the concentration of the ions, in which case you would need to put it in there. But X is the solubility. Okay? So let's try a little bit different one. Calcium carbonate, we talked about that before. It's coral reefs. So we're going to start by writing the reaction, CaCO3, again a solid, goes to Ca2+, and the ion of which it is made is carbonate. Look on the back of your periodic table to find these guys. I know it's been a long time since we've done them. Okay? Put in your ice table. Actually, I'm putting an IC table. It says calculate the solubility. Solids we don't care about. This one starts at 0, this one starts at 0, gains X, everything has coefficients of 1, so you get X and X. KSP is Ca times carbonate. You get 3.7 e to the negative 15 equals X squared. All I'm going to do is take the square root. You get 6.1 e to the negative 8. And that goes here. Not 18, 8. And this is the solubility. Okay, so it's not so bad. It's a little bit harder, but it's just, generally speaking, it's not too bad. It's not as hard as what you guys might be used to. So this one's a little bit harder. So PB, Br2, again, it's a solid. If I see KSP, I automatically know. It goes to PB2 plus and 2 Br minus. Set up your ice table. Big X underneath my solid. Starts at 0, starts at 0. This one is going to gain X. This one is going to gain 2X because it has a coefficient of 2. Every time one of these PBr2s breaks apart, I get 2 ions of bromide. So you have to watch for that. That's a tricky thing. It's really hard to remember that. X and 2X. So my KSP expression, this is based on how it is calculated, is PB2 plus and Br minus squared. Again, because it has a coefficient of 2, that is how this is calculated by definition. I'll put in my numbers. I got 2.75 e to the negative 17 equals X for the PB, and then the quantity 2X squared. Watch for that. I know that seems weird. I know that seems, wait a minute, I'm doing something twice. And it's 2X here because it gets 2 BRs according to the stoichiometry. It's squared because that's how Ks are calculated. That has nothing to do with the fact that the mole ratio is what it is. It's all about the coefficients, and that's how those are calculated. So what I have is I have 2.75 e to the negative 17. And be careful here. You're going to get 2x quantity squared is 4x squared times x is 4x cubed. So you're going to divide by 4 first. You get x cubed equals 6.88 e to the negative 18. And now you want to take a third root, okay, a cube root. And so there's a couple of ways to do that. If you have a graphing calculator, on the button that says math, there is a cube root. You hit that, and then you put in the answer, and it'll calculate a cube root for you. And that is the solubility. If they asked you for the numbers, you would put in 4x, 1.9 e to the negative 6, and you would put it in here, but don't forget you need double, so it would be 3.8 e to the negative 6. So you want to watch for that, okay? But generally speaking, it's not done much differently. So let's try this one. So the reaction first, FeOH3. I know it's a solid because it says KSP. Double arrows, Fe, 3 plus, and see how there's a 3 outside? 3 hydroxides into the ions of which it is made, iron hydroxide. Set up your ice table. Big X underneath the solid, 0, 0, plus X, plus 3X, coefficient of 3. So at equilibrium you got X and 3X. The KSP is the product, Fe3 plus raised to its coefficient multiplied times the other product raised to its coefficient, which is 3. So we're going to put in those numbers. X times the quantity 3x cubed. And again, I know it seems weird. It will always be that way. The two of them are going to be the same thing. So 3 cubed is 27, not 9. So 27x cubed times x is 27x to the 4th, 6e to the negative 38. Divide both sides by 27. I can't do that on here very well. Oop. So I got x to the 4th equals 2.2 e to the negative 39. I want to take a 4th root. And again, there is a special button on the graphing calculator or called 4. You would type in a 4 and then a x root. Or you can raise this to the 0.25, 1/4 power. And if you need to know how to do this on your calculator, I can help you. 2.2 e to the negative 10. That is the solubility. If they asked you for the numbers, you would put in 2.2 e to the negative 10. And then here you would triple it, 6.6 e to the negative 10. Just have to pay attention to what they're asking about. Okay? Last kind of problem, I think. Oh, we got 2 more. Okay. Now they're telling you what the solubility is. Keep in mind, this is X, is that value. Calculate the KSP. So CuBr, solid, Cu plus, and Br minus. Ice table, ICE. This is 0, 0. This is going to gain X. This is going to gain X, X, and X. KSP, the expression is always products raised to their coefficients, multiplied together, divided by the reactants, which are a solid. But this right here, solubility is X. So KSP is X squared. I'm just going to put that in for X. 2e negative 4, and I'm going to square it. I should get 4e negative 8. And remember, KSP doesn't have units. Okay? So let's try one more. Ni2S, not the solubility. You want to calculate the KSP. Ni2S goes to Ni plus S2 minus, and there are 2 of those Ni's. Set up your ice table. Big X. This starts out at 0. This starts out at 0. This is going to gain 2x. This is going to gain x. KSP expression is based on the coefficients of the products where they're multiplied together. So ni squared, so I'm going to put in 2x, quantity squared, times x, which is 4x cubed. This right here is x. Okay, so when you plug that in, you get 1.35 e to the negative 20. So that, again, solubility is referring to the x value. So once you set this up, all you have to do is plug it in for x and solve. Cube it and then multiply by 4, and that's your answer.